The second part of this lab is actually an investigation of torque and how it affects the angular acceleration of an object. Now remember, torque is defined as a force's ability to cause rotation. And there's a couple things that you have to know about torque. The first thing you need to remember is torque is caused by the portion of the force that is perpendicular to the lever arm. That's why you always have to deal with that angle, right? Okay, but we avoid having to deal with any of that angle stuff by wrapping the string around a pulley, because when you wrap a string around a pulley, it always pulls off tangential to the circle, and that means it's always at a 90-degree angle with the radius. So the lever arm is just the radius of the pulley, okay? And that'll come in handy in a minute. Now, you set this thing up. You're going to have two aluminum discs. There's one with a little hole and one with a big hole. The little hole one gets screwed on using that funny screw, and then you can set the other aluminum disc on top of it. Okay. You have a hanging mass over here. This thing's going to vary between 15 and 80 grams, depending on how much you want to vary the mass. And then you're always going to use the same pulley. You're going to use the bigger step on the 3-step pulley. Okay. Now, it says define the mass of one of the solid aluminum discs. Well, a single disc has a mass of 106 grams. The two discs is 212 grams. Okay. Place enough mass on the hanger so the total is 15 grams. Okay. Then wind the string onto the largest pulley on the rotary motion sensor. Start data collection. Then release the hanging weight. Catch it, and you can catch it before the string completely unwinds. That way, you don't have to try to lock the string back onto that pulley. Okay, but you do want to have data collection occurring while the mass is dropping, while it's accelerating down. Then you're going to get two graphs from that. You're going to get a position time graph, which is really an angular position time graph, and you're going to get a velocity time graph. Okay, your velocity time graph is probably going to look a little bit like this. Okay, you're going to have 0 here. It's probably going to hang out there for a minute, then go like this, and then either flatten back out or maybe it just ends. Okay. You're interested in this portion of the graph, right? This is where you're holding it. This is where you caught it. But right here, this is while it was falling and accelerating, okay? And it might go up instead of down, depends on which way you wound your string, but usually it's a negative velocity, okay? You're going to curve fit that, right? So you highlight that portion of the graph, then you do analyze, curve fit, velocity, choose fit, and it's going to be, that looks linear, so you're going to do a linear fit, okay? Because the slope of a velocity time graph is acceleration, you want the m, right, the slope of that, and you'll record that right here in this data table. Then put the second disk on there, repeat the process, and record that here. Then change the mass, whatever it is, change it. You can go 20, you can go 25, you got to change it a few times. And again, you're going to test a single disk and both disks, a single disk and both disks, a single disk and both disks. Okay, so you're going to have several trials to do where you collect data. Then it says, okay, now, did the disks oppose the motion of that falling mass? Okay, and if they did, how can you tell? If they didn't, how can you tell? Well, I want you to think about it. I'm not going to tell you the answer. I want you to think about it. But if that mass is falling unopposed, then its acceleration should be the same no matter what, right? It doesn't matter. Two objects fall at the same rate, whether or not they're the same mass, if they're in free fall. Right? So basically this is asking you, is this thing in free fall? And if it's not in free fall, does changing the disks affect its acceleration? Okay? And I think the answer there will be pretty obvious. In order to find the relationship between torque and angular acceleration, we need to derive an equation for net torque because we didn't measure it. Okay? We measured the angular acceleration of those rotating disks, and we know the mass of the hanging mass, but we don't know the net torque. Okay, we were not able to measure the torque directly, so we have to derive an equation to get it. This is a little bit fuzzy. Okay, now let's start with a case we're more familiar with. Okay? If you think about this, there are actually several forces that act on this system. Right? There's the weight of that falling mass, little mg. Then there's the tension in the string over here, Ft, and that tension is way over here, which is also Ft. Okay, but we're going to ignore friction for now. So that's the only thing, that's the only forces acting on that cart. Now it says we want to derive an expression for the net force acting on the cart. What can we say about Ft? Is Ft and mg the same size? Well, we know they can't be. If they were the same size, then these two forces would exactly balance and this thing wouldn't move. Okay? There would be no acceleration, so this thing would just sit there. But we know when we let go of the cart, the mass falls, it accelerates to the right. Okay? So we know Ft has to be less than mg. Okay? And so by a similar process, we know that the string that was wrapped around the pulley, okay, yes, it was exerting a torque, but the force right here can't be equal to the mg, the weight of the hanging mass. Okay, so how do we get an expression for Ft on the cart? Well, the net force on the cart is equal to Ft, which equals the mass of the cart times its acceleration. But we're stuck with that. Okay, that didn't help me a whole lot. So let's come over to the hanging mass. Okay, the hanging mass over there, I have the net force is equal to well, now I want to pay attention to direction. I just said that this was the way the cart was accelerating. I called it positive. Okay, the pulley switches that and makes this way the acceleration. So now actually I'm saying down is positive, but that's okay. Okay, so the net force is equal to mg minus Ft, and that equals ma. Okay, where m is the mass of the hanging mass, because everything over here is the hanging mass. Okay, and so then I'm going to add Ft over to this side and subtract ma over, and I get Ft is equal to mg minus ma. Okay, so the tension force is given by gravity minus the acceleration, or mass times acceleration of the hanging mass. Okay, so this is the equation that allows me to find the net force acting on this cart. Okay, now we're going to do a similar process down here on the hanging mass, on the disc that's being accelerated. Okay, and so it says we can apply the same principle to determining the torque applied to the discs by the hanging mass. We know torque equals force times lever arm. So now I'm going to think about on the disc. Okay, we had this big disc right here, and underneath it there was a pulley, and on that pulley there was a string, and that string, okay, we're looking at a top-down view, was pulled this way by the hanging mass. Okay, so this is the tension in the string, and that tension is the force that's causing torque. So if I look at that, the net torque acting on the hanging, or on the pulley, is given by the force, the tension force in the string, okay, times the radius of the pulley. Okay, so I get net torque equals Ft times r. Now, since the hanging mass and the discs were both accelerated, we have to account for both of them, just like we had to account for both the masses up above. Okay, and so what we're going to do is we're going to sub in the equation that we have from up above right here. Okay, only the masses are a little bit different. Okay, so we're going to say net torque is equal to the tension force, but the tension force is really the hanging mass, m, times g, minus the acceleration, a, of the hanging mass times the hanging mass. Okay, and all this is multiplied by r. So this equation right here just got subbed in right here. Okay, now remember, this m is the hanging mass. Okay, and that matters. Alright, so the net torque causing those discs to rotate is given by mg minus ma times r. Okay, now it says use what we know about the angular and linear acceleration to derive a similar equation to the one above for the net torque acting on the discs. Okay, and so we had everything in angular acceleration, so we're going to try to put that into angular acceleration. So I'm going to say net torque equals mgr, I'm distributing that through, minus ma times r, except we don't know a, we know alpha, we know angular acceleration, but we know this equation, alpha r equals a. So I'm going to sub that in right there, and so I'm going to get net torque equals mgr minus m alpha r r, or m alpha r squared. Okay? And so I have this nice equation. This is the net torque acting on that disk. The net torque is mgr minus m alpha r squared.